United States Air Force Instrument Pilot Instructor School is conducting an intensive research program to investigate, from a pilot's point of view, the problems of landing under minimum weather conditions. There are increasing operational requirements for landings during minimum weather conditions. Few pilots, however, have had the opportunity to familiarize themselves with a low visibility environment at or below existing minimums. Actual experience is needed not only to determine the problems that actually exist, but also to further define the pilot's role during all weather landings. What problems will confront the pilot? Are there sufficient visual cues to land the aircraft safely? If so, how will the pilot use them in conjunction with his instruments, and what crew procedures will apply? These are a few of the questions the Landing Weather Minimums investigation is attempting to answer. This film represents the preliminary results of this investigation and shows the various weather conditions and related problems a pilot may encounter. The project approaches were flown using an experimental instrument system developed by the Air Force Flight Dynamics Laboratory. This conceptual flight control display system permitted the pilot to make meaningful control inputs through touchdown on instruments alone. The instrument system included a manual and automatic ILS approach and landing capability, an experimental attitude director indicator, an approach sequence indicator, a lateral situation indicator indicating the center of the runway, and conceptual displays of flight path angle, instantaneous vertical velocity, and radar altitude rate. In addition, for photography purposes, a radar altimeter was used to indicate height above terrain as the aircraft progressed along the approach. With the pointer at 12 o'clock, the aircraft was at 200 feet. At 9 o'clock, 100 feet. At 7:30, 50 feet over the runway threshold. At 6 o'clock, touchdown. This system is still being developed, with recommendations to be made based on actual weather experience gained from this project. The preliminary flying phase was concluded in mid-1967. More than 100 approaches and landings were made in weather conditions below existing minimums to determine the visual cues available in the low visibility environment. These cues include the approach lighting system and the runway lights and markings. This approach lighting system is the United States Standard A configuration, 3,000 feet long. It consists of centerline lighting with lights spaced 100 feet apart, 1,000-foot bar, sequence flashing strobe lights, red terminating bar and red wing bar lights. Runway lights include threshold lights, high-intensity runway lights spaced 200 feet apart, and on some runways, touchdown zone and centerline rollout lights. Runway markings include overrun markings, threshold markings, runway direction number, landing zone markings, centerline markings, and side stripe markings. Another type of visual cue is the contrast between the runway and its surroundings, as depicted here. Needless to say, visual cues that may be seen in daylight may be entirely lacking at night. The first series of approaches show the visual cues available during approaches to existing minimums.
Pifax 60, Vandenberg weather. Partial obscured. Measured 300 overcast. Visibility 3/4 of a mile. Fog. Runway 30. Visual range 5,000 feet.
RVR, or runway visual range, was obtained electronically, and for the test an observer was stationed near the approach end of the runway. However, neither observation represents the pilot's slant range visibility, or the visibility along the entire runway. In this first approach, the aircraft was purposely offset to study the recognition of visual cues when misaligned. Notice how the cues gradually come into view. Fortunately, the crew knew where the runway was. The decision to continue such an approach involved not only the visual cues, but also the degree of correction necessary to align the aircraft with the runway. The integration of visual cues was complicated by the weather. Project pilots encountered three types of low visibility: a cloud-based condition, a deep fog, and a shallow fog. First, the cloud-based condition.
PIFAX 60, Andrews weather, measured ceiling 200 overcast, visibility 1/2 mile, fog, runway 01, visual range 5,000 feet.
Approaching 200 feet, the visual segment, or forward visibility, increases very rapidly. Approach lights, then the entire runway environment. Deep fog was similar to the cloud-based condition, but instead of a clearly defined breakout after visual contact, the visual segment gradually increased, reaching a maximum just before touchdown.
PIFAX 60, Mather weather, indefinite ceiling 200, sky obscured, visibility 1/4 of a mile, fog, runway 22, visual range 4,500 feet.
Approach lights. Notice how the visual segment increases. 13 seconds from 100 feet to touchdown. No margin for error. Decisions must be prompt and accurate. Shallow fog presented an entirely different situation, as visual contact with the approach lights was established early. But as the aircraft descended, the visual segment decreased to a minimum just after entering the fog.
PIFAX 60, McCoy weather, partial obscured, visibility 3/8 of a mile, fog. Runway 36 left, visual range 2,000 feet.
Weather observations in one area may not coincide with what you see on final approach or landing because of the varying character of the fog. 300 feet. The lighting system is in view. 200 feet. Notice how the visual segment decreases. 100 feet. The visual segment increases. As experience was gained in low visibility conditions, the transition to and integration of visual cues became less difficult in the time available.
PIFAX 60, Randolph weather, indefinite ceiling 200, sky obscured, visibility 1/4 of a mile, fog, runway 32, visual range 1,600 feet.
200 feet. Small correction. Approach lights. Cross-check. Touchdown. Flying actual weather approaches emphasize the importance of crew coordination. By sharing responsibilities, the pilot has more time to assess the situation, improving the quality of decisions.
PIFAX 60, Mather weather, indefinite ceiling 100, sky obscured, visibility 1/8 mile, fog, runway 22, visual range 1,200 feet.
In the experimental phase, the following crew coordination procedures were used. One pilot flew instruments to touchdown. The other cross-checked instruments to 200 feet, then came heads up to identify the visual cues as they appeared. Other crew coordination concepts are being evaluated to develop optimum in-flight procedures. The next sequence shows visual cues during approaches below 1200 RVR. It identifies some of the hazards involved and the availability of the visual cues.
PIFAX 60, Randolph weather, indefinite ceiling 100, sky obscured, visibility 1/8 mile, drizzle, fog, runway 32, visual range 1,000 feet.
The problem of rain distorting or blurring the visual cues was accentuated in minimum weather conditions. The windshield wipers were left off on this approach. 100 feet. Threshold. Touchdown. Notice how the visual cues improve when the windshield wipers are turned on. On several occasions, visual cues were adequate for lateral control, but unusable for pitch control. Accurate visual pitch control was not possible until both the runway and the pilot's aiming point were in view.
PIFAX 60, Castle weather, partial obscured, undetermined overcast, visibility 1/8 of a mile, fog, runway 30, visual range 800 feet.
Again, shallow fog. Approach lights are in view. "100 feet. Are the cues sufficient to flare the aircraft? Consider now deep fog with the same RVR as the previous approach.
PIFAX 60, Randolph weather, indefinite ceiling 100, sky obscured, visibility 1/8 mile, fog, runway 32, visual range 800 feet.
Again, the difference between the deep fog and the shallow fog. Notice how the visibility increases. Other aspects that became increasingly significant were runway contrast and background brightness. At times during daytime operations, runway markings were the only available cues.
PIFAX 60, Mather weather, indefinite ceiling 0, sky obscured, visibility 0, fog, runway 22, visual range 500 feet.
100 feet. There is about 7 seconds from 50 feet before touchdown. The shallow fog was found to be the most hazardous because a premature decision to continue the approach could lead to a dangerous situation.
PIFAX 60, Castle weather, partial obscured, visibility 3/16 of a mile, fog, runway 30, visual range 200 feet.
Assume that you are flying this approach. At 200 feet, would you continue? Approaching 100 feet, what would be your decision? "50 feet. Touchdown and rollout was completed on instruments. Experience also was gained in performing a missed approach in minimum conditions.
PIFAX 60, Castle weather, partial obscured, undetermined overcast, visibility 1/8 of a mile, fog, runway 30, visual range 200 feet.
In early tests, a minimum altitude was established below which pilots would not descend without cues. 100 feet. No cues were visible, so a missed approach was made. Sometimes visual cues did not appear until just before touchdown, requiring the pilot to complete the landing on instruments.
PIFAX 60, Castle weather, partial obscured, visibility 1/16 of a mile, fog, runway 30, visual range 100 feet.
"100 feet. 50 feet. 25. 15. Touchdown. Accurate definition of this low visibility environment is difficult, as fog never is homogeneous.
PIFAX 60, Castle weather, partial obscured, visibility 1/16 of a mile, fog, runway 30, visual range 100 feet.
Someday, an approach and landing such as this may be routine. 100 feet. 50. 25. 10. Touchdown. At this point, definite conclusions would be premature, for many aspects of this unexplored environment need further investigation and study. The landing weather minimums investigation is continuing to explore the low visibility realm, examining the problems of visual cue integration, crew coordination, control display requirements, and the ever-changing complexity of the weather. In the future, a 0-0 landing may be routine, but it remains to be seen what advances in technology are made and to what extent the pilot will be able to rely on them. Instrumentation and guidance systems are not the only answers. Pilot techniques and procedures must also be developed further. Meanwhile, successful minimum weather approaches and landings will continue to depend on the pilot's ability to recognize and use the visual cues available.